Hi, I'm Shane Godmer. In this video, we will cover block diagrams and schematics.
When you really get into radio, you may become interested in how they are put together and what makes them work. You'll learn how to use block diagrams and schematics. We'll start by building a ham radio station using a block diagram. Usually, when a radio operator starts to think about a radio station, the transceiver is the first thing to come to mind. You'll see lots of them in a ham radio station. We'll lay down this label, transceiver, as part of our radio station block diagram. Most hams will use a microphone like this to connect to the transceiver to convert voice into radio waves. We'll connect the microphone label to the transceiver in our block diagram. Many ham radio operators will want to add an amplifier to their radio station. Why might you think they would want an amplifier? For our station here, we'll connect our transceiver to an amplifier label. All ham radio stations use some sort of antenna to radiate the signal. Here, in our block diagram, is the antenna. We'll connect the amplifier to the antenna with a special kind of cable called a feed line. The feed line carries the amplified radio signals to the antenna. There you have it, a basic ham radio station in a block diagram. The block diagram gives you a high-level picture of the ham radio station system. As you become more interested in how things work, you might become familiar with schematics. Schematics are the map of the electronic components inside a device. Next, we'll look at schematics. The schematics map out the components in our transceiver and how they are connected. This is very helpful when troubleshooting the equipment. You can't really repair a complex device like a ham radio transceiver, or even a simple one for that matter, without knowing how to read and use schematics. If you want to learn more about schematics, the Electronics Merit Badge can help you get there. You can see if we just shrink the size of our schematic to make it part of the block diagram, it really doesn't help us. The block diagram helps us at a high level, seeing the whole system in an easy-to-read manner. Before you become knowledgeable about electronics, components, and schematics, a block diagram should help you understand how a radio system goes together. Let's look at how information is transmitted, how radio waves carry information. When we talk, the variation of our vocal cords creates sound waves. That is how you can hear me right now. The waves on the screen represent an audio wave. It is what we want to transmit from our radio antenna. One way we can transmit the audio is to use amplitude modulation, or AM. If you look closely at the AM radio wave, you'll actually see three waves. The higher frequency radio carrier wave, that is the transmitter sends to the antenna, and our original audio wave duplicated with the top and bottom of the carrier. When we say amplitude, vertical height of the carrier changes according to the audio signal it is carrying. When you listen to AM radio, your radio receiver is detecting this kind of wave. Now we see a totally different way to carry our voice. Frequency modulation, or FM. Note how there are three moving illustrations here to compare. Different than AM, the FM signal keeps the same amplitude but changes its frequency with each change of the voice signal. There are advantages and disadvantages to AM and FM, but we don't have time to talk about it here. But at least you can easily see how they are different. These are only a couple ways the information can be sent over the airwaves. Let's study some more. To look at our next mode of transmitting information, we'll bring back up our amplitude modulation diagram. Our next mode is single sideband, or SSB. Notice you're not seeing anything right now. That's because no one is talking into the microphone. In the AM signal above, there is always a carrier transmitted, even when no one is talking. Once you start talking in an AM transmitter, the carrier is then modulated as shown. But in a single sideband transmission, nothing happens on the airwaves unless you talk. Here, we're showing the single sideband signal that matches the words that are being spoken into the mic. Single sideband is more efficient than AM. Let's look at another way to send information in our transmitted signal. This image shows an actual scan of a different kind of radio carrier wave. It's called continuous wave, even though you see breaks when we turn it on and off. The name might be a little confusing. If ham radio operators wanted to, they could transmit a solid continuous tone wave like this one. He breaks up the continuous wave for a reason, though. Can you guess what that reason might be? When one of these little pieces of continuous wave is detected by a radio receiver, it makes a short dit sound. If the operator strings 3 of these short bursts of continuous wave, it creates 3 dit sounds. A slightly longer burst results when the operator calls for a dash or a da. What we see here, the operator can send in continuous wave dit 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 da. What information do you think the operator is sending? The operator is sending Morse code for the letter V. We ham radio operators refer to sending Morse code as CW. What does CW mean? CW was the first form of messaging on the airwaves. In a sense, it was also the first form of digital communication. This was a typical Morse code and semaphore aid for scouts in the 1940s and 50s. We won't say much about semaphore, since it is covered in the Signs and Signaling badge. Morse code or semaphore were once requirements for scout rank. Morse code goes way back to the 1800s. Find the letter V and you'll see those 3 dits and 1 da, as we just talked about. Let's look at one more. Take a look at the string of CW dits and das. What might the operator be sending? Now let's compare a couple of radio wave signals and get an idea of what might be going on. First, we have a typical continuous wave. There is no modulation, that is, no dis and das being sent. If you could hear it, it sounds like a continuous tone. Compare your continuous wave to this one. What is the purpose of this wave? What kind of wave is being transmitted? Let's take a closer look at this digital radio wave. The wave consists of 2 different elements, a short burst and a longer burst. In this particular type of digital signal, and there are many others, the first part of the short burst takes 58 millionths of a second to happen. The first part of the longer burst takes 100 millionths of a second to happen. Not quite twice as long as the short one, but long enough to be different. The computer and its software is connected to knows how to detect and separate these bursts. The first short burst is associated with the number 1, the second longer burst associated with the number 0. The whole string of bursts then reads 1110100. This is a base 2 number for 116, and it could be a code for some command or other information for the software. To help understand how all this works, let's take a look at one example of digital communication in action. Here's a very simple digital communication system connected with wires or possibly fiber optics. In this example, we are sending some sort of digital information from A to B. We use a computer to create our information message and an encoder to change the digital data to some form of signal that can be sent over the wires or cable. The digital signal is picked up by the decoder at B and sends the decoded message to the computer at B, where the operator can somehow read or use the data. Now let's replace the encoder and decoder with radios that are set up to do the same thing. Of course, radios don't communicate by wire. Instead, they transmit and receive radio waves over the air. Antennas are used to transmit the signal and receive it. Now, the same signal that was shared through wires or cable is now sent from one antenna to the other. We are no longer relying on the infrastructure of wires and cables. This is a very big deal. Where most communication systems rely on wires or cables, ham radio signals can be entirely off-grid. In a major disaster or emergency, this comes in very handy. NOAA Weather Radio is a network of radio stations in the United States that broadcast continuous weather information directly from a nearby weather forecast office. NOAA Weather Radio broadcasts National Weather Service warning, watches, forecasts, weather observations, and other hazard information 24 hours a day. It also broadcasts alerts on weather emergencies such as national security, natural, environmental, or public safety throughout the U.S. This is managed under the Federal Communication Commission's Emergency Alert System. There are many special radios designed to receive NWR broadcasts. One of these radio receivers could be a great addition to your home emergency kit. As we mentioned at the beginning of this course, most of us use radios every day, even though we are not a ham radio operator. We use cell phones. Ever see one of these someplace in your town? What is it? Cellular telephone base station antennas like this one are located in more places than you can imagine. We take them for granted, but it is an interesting technology. They send and receive communication signals 24 hours a day. A mobile phone or wireless device is a low-power, two-way radio operating at a maximum of a couple of watts. Most of the phone is a battery, strong enough to make several calls, send lots of text messages, search the internet, and take photos with the camera. The phone has an audio circuit that includes a microphone and a small speaker. Some have earphone connections, and others use Bluetooth to send audio signals to a wireless earpiece. Bluetooth is yet another form of digital radio. Of course, the phone has a computer with lots of memory. A cell phone has more computing power than the computer used to send people to the moon. The phone has a transceiver section one that transmits and receives signals. Finally, no radio system would be complete without an antenna. Yes, cell phones have built-in antennas. Mobile phones have become more important for all things we do besides making a phone call. Let's look at the basics of a cellular telephone system in a make-believe town. First, we got these base station antennas. Wireless companies locate them in the best possible places, considering population, obstructions to signals, and available property. We're just showing 4 base station antennas here, but they're usually enough to cover the entire town. Now we're showing the cells that are covered by the base station antennas. A cell is as big as the range of a base station antenna. Here we're showing they reach out in the same distance, but in reality, distances can vary quite a bit. If we want a bigger cell, we can increase the power of the base station transmitter. For this discussion, we're showing how the same range. The base station antennas are wired directly to the cell carrier's network, which ties the base stations together around the country. The cell carrier's network is also tied to other carriers' network through the standard telephone system, the public switch telephone network. When your phone is turned on, even when you're not using it, it tries to link up with the nearest base station. How well it's doing is usually indicated by the bars on your phone. When you call a friend up here, he is close enough to the base station to have a very good connection. He probably won't experience a drop because he has a strong signal. But when you call a different friend down here, his location is on the edge of a cell, and no other base stations are nearby. His call may drop. And when you're trying to call another friend down here, his cell phone will not pick up the signal because he's out of range of the cell tower. His phone will probably indicate no signal or out of range. We could talk a lot about the differences between using mobile phones and ham radio during disasters, but let's look at some big differences. Cellular systems during normal use are handling large numbers of regular calls, around 90% load. We've learned that cell systems are quickly overloaded when a disaster occurs. If twice as many people tried to access the mobile phone network, it would be loaded at 180%. It won't work. The only real load with ham radio is the ability of trained hams to operate under emergency protocol. Cellular systems do have a wireless component, as we've already discussed. We've also mentioned that they use landline telephone system to be functional in order for the cell phones to work. Ham radio does not have such a requirement. Cell systems also require electrical power. Ham radios do as well, but can easily be functional with batteries or portable generators. Cell systems do not have this capability.